I want to continue discussing operators today. And so operators in quantum mechanics don't all have to be observable. Some operators, for example, might just rotate state kets in the Hilbert space. Okay, and so we distinguish between two kinds of operators in particular. And those two classes are Hermitian and non-Hermitian. Okay, and the distinction is if it's a Hermitian operator, the eigenvalues are real. And these are observables and are observables. So the eigenvalues are real for Hermitian operators. Non-Hermitian operators, they can be real or non-real. Real or imaginary. And in particular, though, all observables are represented by Hermitian operators. Okay, so this is a big distinction, and it's an important one. So let's see how we define a Hermitian operator. First, we have to define what's called the Hermitian conjugate. Okay, so we'll take A as just some operator that operates on a Hilbert space, and what we want to do is just define what the Hermitian conjugate is. So we do the following. Let's let two kets, phi and psi, be in the Hilbert space. Now, we can write, I can write the operator A on phi. This is just some ket in the Hilbert space. I'm just going to write it with A inside the ket itself. Okay, this is just some new ket in the Hilbert space. Okay. So I might as well be able to just write it like this. You'll see here why I'm doing it in just a second. So now let's consider the amplitude that's given by psi a phi. Okay, this is some complex number in general. Now, if I write this in terms of components, this is equal to the sum over I and j of psi star I a I j phi j. Okay, I'm just writing this now as, you know, this is a bra, psi is a bra vector, so it's psi star 1, psi star 2, and so on. And then I have a matrix A, A11, A12, and so on. And then we have phi, which is phi 1, phi 2, and so on. So I'm just writing out the matrix notation. Okay. Now, what I want to do is I want to see what happens if I bring I have A here sort of operating on phi first, maybe, if you want to think about it that way. And I want to just kind of turn things around here. So what I can do is I can just rewrite this expression. I can rewrite this as the sum over I and j of, first let me rewrite it here. This is the sum over I and j of psi I, aij star, phi j star, and then I can star the entire parentheses. Okay. And then if I want to write it the other way around, I'll have phi j star on the left. I can swap the indices here, I and j, and take the transpose. So I can write this as aji star transpose, and then times psi I star. Okay. So now what's this? This is just, if I sum over all of this stuff in here, this is a transpose, and with the star, there's a dagger here acting on psi. So this is phi, a dagger, psi, with the star. Okay, and now remember that if I take a ket, I take an amplitude and I want to flip it around, I conjugate it. So this is just equal to a hat dagger psi acting on phi. Okay, and so I have this particular relationship here. I can write this amplitude as psi a hat phi, but that was equal to this, which is a hat dagger psi phi. Okay, this equation defines the Hermitian conjugate. A hat dagger. All right, what did I do? We moved it from acting on phi to acting on psi. And that's defines the Hermitian conjugate, okay? So this is some other operator. All right, in general, it's not the same operator. If they happen to be the same operator, then A is called Hermitian. Okay, so it's not always the same operator. It's in general not the same operator. But if it is the same operator, if when you do this and you get the same operator, then that operator is Hermitian. And what's important here, over this point here, Hermitian operators have real eigenvalues. So let's see that. Okay, so let's suppose that we have a set of basis states for A. Eigenkets for the operator A, and that A hat dagger is equal to A hat. Okay, so we have a set, say phi I, such that A hat on phi I is equal to lambda I phi I. Okay, then if we look at phi I, let's consider what phi I. What is this expectation value in this particular case, because we have the same ket on both sides? This will just be phi I, A, now when A operates on phi sub I, it just gives lambda sub I phi sub I. So this is equal to just lambda phi sub I phi sub I. So we can assume that this is just 1 if they're a normalized set. And then, well, what is this? This is equal to phi I A hat phi I, right? I'm just rewriting it by putting A inside the ket over here. And this is equal to A hat dagger phi I phi I, by definition of the Hermitian conjugate. But A is equal to, A dagger is equal to A, so this is just A phi I. But now I can just rewrite this as phi I A phi I star, by just flipping the Braun-Ket around. So this will be just lambda I star. So lambda I star, lambda I equals lambda I star, and it's real. Okay, so Hermitian, that's what we want in an observable, because we want, if we make a measurement, so something that can be associated with a measurement is an observable that gives a real number out, and so that means it's a Hermitian operator. So Hermitian operators are what we associate with measurements. Okay. Are there any questions right so far? So we're going to meet now some non-Hermitian operators in a little bit. So now let's see. Let's talk about for a moment the phase of a state vector. It's any factor. Okay, so if I said that if psi is some state vector, then e to the I alpha times psi represents the same state. Okay, and here alpha is a real number. Okay, and that's because of the following. If I could, suppose that O hat is some operator, some observable. Then the expectation value of O will be psi O hat psi, or if I have this state vector with the e to the I alpha in front of it, a phase, that will be psi e to the minus I alpha O hat e to the plus I alpha psi. And they will be the same because the exponentials here will cancel out. So we'll have e to the minus I alpha O hat e to the plus I alpha this is just equal to e to the minus I alpha, e to the plus I alpha O hat, and this is just equal to O hat. Okay, so the phase of a state kit is, will not affect measurements. It's not an observable. Okay, are there any questions so far? All right, let's look now at, now we'll start doing some real work with operators. All right. So we looked at, well, we defined the spin of this electron, or the spin 1/2 particle, had two possible states. It had, spin up or spin down, but we could do that in 3 different sets of basis states that depended on the orientations in 3 space that we had. So now what we want to do is consider some operators that will operate on our base states and are going to represent some rotation operators. Okay, but they're not, these are not, they are rotation operators, but these, you'll see that this is, quantum mechanics here becomes very different than rotation that you think of in normal 3-dimensional space. So let's build some rotation operators. For spin 1/2. Particle base states. And that would be the states x plus minus, y plus minus, and z plus minus. Okay, and recall that we had we found the spin operators Sx hat, Sy hat, and Sz hat. That they satisfied this relationship, Sx, Sy was equal to I h bar Sz. And then if you just cycle x, y, and z in this order, then you have the 3 relationships. Okay, and we said that these were generators. Of some angular momentum. Okay, because that's, well, if you took, if you study the angular momentum operators in 3 space, or just rotation in regular 3 space, you have the same set of generators. I'll show that in a little bit, but. So these are generators of some angular momentum, the spin angular momentum. So if they're the generators of the spin angular momentum, then we should be able to use them to generate rotations. So let's use them to generate rotations. Of the basis vectors, of the basis kets. Okay, so let's do this now. Okay. So let's start by renaming them. So this is just so they conform with standard usage here. So we'll write JZ hat is equal to SZ hat, JX hat is equal to SX hat, and JY hat is equal to SY hat. And now let's consider a rotation about Z. And let's call the operator RZ hat of, say, some angle phi. Now, we would expect the following. If I let this operator RZ of phi operate on Z plus, so what do you think I should get if I just let an operator that rotates about the Z-axis and it's operating on Z plus? What's just a good guess of what this might be?
Try and get it to switch to another axis, like just shift over one, or?
Well, if I've got something that's pointing along the Z-axis and I rotate it about the Z-axis,
it doesn't change, right? It's still just Z plus.
right?
Oh yeah.
Okay, but we can introduce, it might introduce a phase, which is an unobservable thing, but we have to allow for that fact. So we expect that this thing could be some e to the I, some function of phi times Z plus. This could introduce a phase. Okay. And so if we took this new ket and take the inner product with itself, so if I turn this around, now I'll have Z plus. And again, you can imagine just sticking R, inside the ket here. When I flip the whole thing around to take the bra, that's going to just turn this into an R hat dagger. Okay. So I'll have R hat dagger Z, R hat Z, and then Z plus. And this should be, if this thing is unobservable, which it is, then this should just be 1. Okay, so this. So let's define then, define RZ hat for infinitesimal angle. And so for that, let's write it as RZ hat of d phi, let's call it d phi. So I'm going to write it now. This, I'll write it first, this will be 1 minus I j hat z over h bar times d phi. Okay, now JZ is a matrix, so this is actually, this 1 is actually the unit matrix. This is a 2 by 2, this is 1, 0, 0, 1. If j hat z is equal to h bar over 2, 1, 0, 0, minus 1. Okay, it has to be a matrix. Okay. Now let's recall e to the x is the limit as n goes to infinity of 1 minus x over n to the nth power. Okay, so what I want to do is, what we've done, we've defined an infinitesimal angle here. So to build up a full, a finite rotation, we can break it up into n goes to infinity infinitesimal rotations. So we can write d phi is equal to phi over n. Okay. So then we would have RZ of phi. This would be RZ of d phi to the nth power. So that would be this 1 minus I j hat z over h bar phi over n to the nth power, and we just let this go to infinity. Let n go to infinity, and then we have that RZ phi is equal to e to the minus I j hat z over h bar times phi. So this is that's the definition of the rotation about the z-axis. Okay, are there any questions about that?
Is that something Where is this H part? For the
Just-
RC?
From the definition.
Okay, it's just that.
Okay, so now, so we know JZ. Is equal to H bar over 2, 1, 0, 0 minus 1, so let's calculate RZ of phi. Okay, as a matrix. So let's see what we have here. In the exponent, we have J hat Z over H bar. So if I take out the H bar, I just have a half 1, 0, 0, minus 1. Okay? And so what do we have here? We have RZ of phi is equal to E to the minus I over, so I already took care of my H bar, minus I phi over 2, that's the 2, times this matrix 1, 0, 0, minus 1. Okay, so it's the exponential of matrix. So the only way to define this is to just use the expansion. E to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, dot, dot. Okay, and we'll just calculate it. So first of all, let's see what we get. Let's just examine the matrix. We're gonna have to take this matrix to different powers. So what do we get when we do, so for the first power, it's obviously just this matrix, but for the second power squared, we'll get 1, 0, 0, minus 1. This will give us 1, 0, 0, 1. Right? So this is the square. So block squared is equal to that. So when we cube it, that thing cubed is just going to be the identity matrix 1, 0, 0, minus 1 times the identity matrix 1, 0, 0, 1. So this will just be 1, 0, 0, minus 1, and then we're back to where we were. So if we take it to the fourth power, then we'll just get the identity matrix. Okay, so for odd powers, we just get the matrix back. And for even powers, we get the identity.
Wait, what goes in those parentheses?
Just the 1, 0, 0, minus 1.
Oh, those are the matrices. I see.
Yeah.
Okay.
Okay, so now we can go ahead and write it out a little bit. So we have e to the minus I phi over 2, 1, 0, 0, minus 1. This is equal to the identity matrix first, so 1, 0, 0, 1, plus the whole thing up here, which is minus I. So I've got a minus I. Let's bring it all in here. Minus I phi over 2, 0, 0, plus I phi over 2. Okay, now I have the square divided by 2 factorial. Oops, so I've got plus, I've got an extra half here, and then I've got the square in here. So if I square this I phi, I've got a minus I, there'll be a plus I squared, I'll get a minus. It's be a minus phi squared minus phi over 2 quantity squared. 0, 0, and then if I square this, I'll have a minus. Wait, let's see here. Yeah. Minus phi over 2 quantity squared. All right, let's see. Yeah, that's right. Okay. And now we have to take this, the next term is the cube. So this is, I need a 1 over 6 plus 1 over 6, and then we'll have the cube. Oh wait, let's see. When I squared it, those have different signs. And then I squared it, and I got the same sign there, and then now I want to cube it, and I'll be back to a minus 1. And then I'll have this cubed, so that will be minus I cubed. That will be I squared times minus I. That's plus I. So I phi over 2 cubed. 0, 0, and then this will be, let's see, the cube, I got a minus 1 here. So I think it's just minus, I think I just changed the sign. Minus I phi over 2 cubed. And then plus the next set of terms. So let's go ahead and write out what it is. So we can just collect the terms. So we'll have e to the I minus I phi over 2, 1, 0, 0, minus 1, is equal to, now we'll have 1 minus, let's collect the real parts. So here I've got, this is imaginary, I'll collect the real part here. It's minus phi over 2 squared, and then I'll have, in this term, I'll get plus something else, and then, okay, so I'll have I will have a real part here, and then I'll have some imaginary parts. This will be minus I, and then I'll have phi over 2 plus, let's see here, wait, there's a, hang on a second, let's see here. So this is, plus 1, is that right? 5 plus 1, 6, phi over 2 cubed. Okay, so we'll have this, and then a 0 here. And then we'll have a 0 here, and then we'll have, on the bottom half here, we'll have 1 plus, let's see, this has to be minus. Yeah. Minus phi over 2 squared, and then we'll have a plus. cubed plus dot dot dot. Okay. Okay, so this is how you calculate the matrix representation. So this here is the beginning of the cosine. This is cosine phi over 2, and this is sine phi over 2. So what the matrix is, so RZ of phi is equal to cosine phi over 2 minus I sine phi over 2, and then cosine phi over 2 plus I sine phi over 2. Okay, and so this is e to the I phi over 2 e to the minus I phi over 2. Okay, so that's the matrix representation.
Excuse me, so that note you made, beneath the sums in that matrix, the big one?
Yeah.
So those brackets are cosine and sine?
Yeah.
Okay, they're just expanded, okay,
Yeah, if you were to just keep calculating the terms, you'll get,
okay. Oh, that's one matrix, element.
this is just the first matrix element of the
Okay.
whole thing. It's in the upper left corner. So I'm just picking off, I picked off the 1, and then I'm picking off this term. You know, I'm picking off all the reals and putting them here. And then this term has an imaginary, and this term has an imaginary, so I'm putting those here.
Yeah, okay.
And so you end up getting the expansions for sine and cosine.
Yeah, pick a bad time to go to the bathroom, just saw that.
Oh, yeah. So this is the matrix representation for RZ. Okay, so, oh, did I get that backwards? Yeah, this is minus and this is plus. Okay, so this is where you can see that there's something strange about quantum mechanics here, because what is RZ of phi equals 2 pi? What is that? If I rotate by 2 pi, well, let's see what happens when we rotate the state ket z by 2 pi. So RZ of 2 pi on the state ket z plus, that's equal to e to the minus I pi, 0, 0, e to the I pi, operating on 1, 0. But e to the minus I pi is just what? It's minus 1. So this is minus 1, 0. So this is minus the z plus. Okay, so a rotation by 2 pi, you think of that in 3 spaces going all the way around. But here it does not. It takes it to minus z plus. So it takes a rotation of 4 pi, RZ of 4 pi on z plus equals z plus. Okay, this is weird.
Is that why they're called spin 1/2 particles? Because you have to,
No, they're called spin 1/2 because they have 2 states. This rotation property is, what distinguishes the quantum mechanics of these particles from a real space 3-dimensional rotation of some object. So they're not, they don't behave like that. If you want to bring the state of the system back to itself through rotation, you have to go around 4 pi, you have to do it twice. Okay, and this is this 2 pi 4 pi thing is it's a really interesting topological thing. Okay, so you can actually do this if you have time. It's not actually all that hard to do, but if you had a box and you had a sphere in the box and you have strings or rubber bands attached to the sphere. And you can have as many as you want in here. If you rotate the sphere by 2 pi, obviously you can't really untangle it, it'll just be a mess. But if you rotate it 4 pi, it's easy to untangle it. And you can go right back to this without having to cut the strings or anything like that. They won't get tangled up. And it's a topological theorem, and it only works in certain dimensions and things like that, but happens to work for quantum mechanical particles of spin 1/2. Okay, any questions so far?
Let me get a picture of that before you erase it. Thanks. Okay.
Okay, so let's see what happens if we rotate another state vector. Let's rotate the x. So let's do a rotation, well, let's just do it in general here. So this will be e to the plus or minus I phi over 2. E to the plus I phi over 2. Now, x plus, remember, is 1 over root 2 z plus plus z minus. So I can write 1 over square root 2 here, and then this will just be 1, 1. So what does this give? This will give 1 over root 2, and then we'll have the e to the minus I phi over 2 e to the plus I phi over 2. So that's just the general state kit. And now one thing we can do is to pull out a factor of e to the minus I phi over 2. So I can write this as 1 over root 2 e to the minus I phi over 2. So I can pull this one out, and that will give me an e to the I phi for the second term here. So 1 e to the I phi. And let's plug in pi over 2. So for phi equals pi over 2, this will be e to the I pi over 4. So we'll have this will be 1 over the square root of 2 e to the minus I pi over 4 times, now I'll have z plus e to the I pi over two will be just I, right? This would be cosine of pi over two is 0, and then plus I sine pi over two, so this is just plus I z minus. So here we have, with the 1 over root 2, and this, we have, that's just y plus, and then we have some phase factor. So this is just e to the minus I pi over 4 times y plus. Okay, and that's what, this is what you would expect for a rotation in 3 space. So if we had x, y, and z, if we rotate about z by pi over 2, it should take x into y. And it does, but it does it with a phase factor. So the phase here is phase angular. Okay. All right, so let's look now at let's look at some properties of the of R sub z. So if I take R sub z hat, dagger, that is of some angle phi, that will just be, I change this, if I take this matrix and I take the transpose, it doesn't change it. So the only thing I get from this the dagger is the conjugate, which I just changed the sign. So this will be e to the plus I phi over 2 and e to the minus I phi over 2. So if we calculate our dagger z times rz, then we will just get 1, 1. And this is called, that's the unit matrix, this is called being unitary. So if I take a matrix, I take its dagger and I multiply it by the matrix. If I get 1, that's called unitarity. And then the other property that we notice is that R hat dagger z is not equal to R hat z. So this is it's non-Hermitian. But we do know, for example, let's look at JZ. JZ was h bar over 2, 1, 0, 0, minus 1. And we do have j hat dagger z equals j hat z. So that's Hermitian. Let's do jy. So jy hat is equal to h bar over 2, 0 minus I 0. So is this Hermitian? If I take the transpose and then conjugate, do I get the same matrix back?
Yes.
Yeah. So jy is Hermitian, and jx is Hermitian also. Okay, so the J's are Hermitian matrices. The rotation matrices are not Hermitian, but they're unitary. Okay, so let's look at, R sub y. So if we do the same thing, this will be e to the minus I j y hat over h bar times phi. And so jy hat over h bar will be 1/2 0 minus I 0. Okay, so we can, now you can go through the steps of calculating the square and all this stuff, so. Let's see here. So jy hat over h bar squared would then be 1/4, and then, let's see here, what is this? I'll get minus here, and minus 1, 0, 0, minus 1, and then jy over h bar cubed is minus I over 8 times 0, 1, minus 1, 0. And then jy to the 4th over h bar, sorry, jy over h bar to the 4th will be 1 over 2 to the 4th times 1, 0, 0, 1. And then, so once you hit the identity matrix, then the higher powers will start going through this list again. So I don't want to, that's, you do the same thing that we did before, and you find that R sub y phi is given by the matrix cosine phi over 2 minus sine phi over 2 sine phi over 2 cosine phi over 2. Okay, and when you get, so this looks very much like just a rotation matrix that you would calculate in 2 dimensions, the sine, cosine minus sine, sine cosine. But again, we have this phi over 2, so you can't, in order to go all the way, in order to go back to the identity, you have to go by around 4 pi and phi, okay? But you can calculate then, calculate the rotation matrix acting on the various kets. Okay, so that's the basics of rotation. We're not done with rotation, but that's the starting point, just to be able to write down the operators and let them act on the state kets. So we're going to use this extensively later on, because these rotation operators rotate the state kets. And so one of the things that we want to study in the future, in the not too distant future, is magnetic resonance. So in magnetic resonance, when you put an electron or anything else, if you put a bar magnet in a field, it will precess. And so if we put our electron in a magnetic field, it will precess. And so we can describe that through these rotation matrices and how they act on the state ket. Yeah.
Wait, so that rotation is unobservable, right? So how do you know it's rotating? It's like a point particle, so like how do you know if an electron's rotating?
No. Well, the electron itself isn't rotating. The spin is precessing.
Oh, I see. So okay.
Yeah.
Like kind of like a top that wobbles like that.
Right.
Okay.
Yeah. And so we'll use that to describe rotation of the spins. So this has major applications in all sorts of areas. So if you do this with nuclear spins, you get nuclear magnetic resonance, which is the magnetic resonance imaging, like when you go to the hospital and stuff, you get magnetic resonance imaging. That's done with water, with protons, so it's really simple. But like I mentioned earlier, magnetic resonance, and you can do magnetic resonance with just about every molecule, every element, there's a lot of really fun quantum mechanics just in describing the spins, because the spins for most elements for most nuclei are not 1/2. They're typically higher than that. They're like 3 halves, 5 halves, 7 halves, whatever. So you can have a whole bunch of spin states, which we'll describe a little bit later. Instead of just 2, you can have a whole range of spin states. And so by playing with all those spin states with magnetic resonance, you can determine the structure of molecules and all sorts of things. And then you can also do electron spin resonance, which is with just the electrons themselves. So it's much higher frequency, but it's also a technique that's used. It's not used nearly as much as nuclear magnetic resonance, but electron spin resonance is still something people do to study things in materials, for example. Okay, so anyway, all this stuff we'll use again a lot. And I want to show you, though, before we go today, actually, what time do we have here? I only have 3 minutes, so I think I'm going to stop and pick that up real quick.
I feel like the thing with the 4π, to get back to where you started, like I've heard, I don't know if it was in another science class or if it was applicable to a different subject, but I know I've heard that. Is it only a quantum mechanical thing, or is there any other spheres of math or science where that as a concept pops up? Maybe I just saw it in a documentary or something. I don't know.
I think